NASA just mapped an alien world in 3D, and it's not what they expected. You know what's funny about exploring alien worlds? We've gotten really good at finding them. Over 6,000 confirmed exoplanets and counting. But actually seeing what they're like is a bit like trying to describe someone's appearance after only hearing their footsteps. Well, based on the sound, I'd say they're wearing boots, probably size 10, and they seem to be in a hurry. Now imagine doing that from 400 light years away. Yet somehow, astronomers just pulled off something even more remarkable. They didn't just hear the footsteps, they made a full 3D map of the entire person. Well, planet. You get the idea. What NASA and its partners just accomplished would have been considered impossible science fiction just a few years ago. Using the James Webb Space Telescope, an international team of astronomers has created the first ever three-dimensional atmospheric map of an exoplanet, a world orbiting a star far beyond our solar system. And what they found challenges our assumptions about these distant worlds in ways nobody quite anticipated. The world in question goes by the decidedly unglamorous name of WASP 18b. In astronomy, naming conventions aren't exactly known for their poetry. This particular planet takes its name from the wide-angle search for planets project that discovered it, followed by the designation of its host star and the letter B indicating it's the first planet found in that system. It's the astronomical equivalent of naming your dog first dog found at Street 18b. But what this planet lacks in naming creativity, it more than makes up for in sheer extremeness. WASP 18b is what astronomers call an ultra-hot Jupiter, and once you learn what that means, you'll understand why expectations needed adjusting. This is a gas giant planet approximately 10 times more massive than Jupiter, our solar system's heavyweight champion. But unlike Jupiter, which takes nearly 12 years to lazily orbit the Sun at a comfortable distance, WASP 18b screams around its star once every 23 hours. That's right, a complete year on WASP 18b is shorter than one of our days. This isn't just fast, it's a speed that has profound implications for the planet's entire existence. To maintain such a rapid orbit, WASP 18b must be extraordinarily close to its star, far closer than Mercury is to our Sun. The result is a world bathed in such intense stellar radiation that its dayside temperatures soar to nearly 5,000 degrees Fahrenheit. That's approximately half the temperature of the Sun's surface. We're talking about a planet so hot that metals would vaporize, rocks would melt into lava, and, as scientists discovered, even water molecules can't survive intact. Located about 400 light-years from Earth in the constellation Phoenix, WASP 18b has been known to astronomers since 2009. But knowing a planet exists and understanding what it's actually like are vastly different propositions. For over a decade, astronomers had estimates of its size, mass, and orbital period. They knew it was hot. They suspected it was tidally locked, with one side permanently facing its star. But the details, the texture of its atmosphere, the distribution of heat, the complex chemistry occurring in different regions, remained frustratingly out of reach, until now. When Ryan Challoner and his colleagues set out to map WASP-18b's atmosphere, they expected to see certain patterns. Theory predicted a hotspot on the dayside where the star's light hits most directly. They expected temperature variations with altitude. They anticipated finding water vapor, carbon monoxide, and other molecules in the atmosphere. These were the safe bets based on years of atmospheric modelling. What they didn't expect was the dramatic evidence of water molecules being thermally destroyed in real time, region by region across the planet. They didn't expect to see such a clear ring structure of cooler temperatures surrounding the central hotspot. They didn't expect the vertical temperature structure to be quite so pronounced. In short, while their general predictions were correct, the details revealed a planet far more dynamic and complex than models had suggested. We think that's evidence that the planet is so hot in this region that it's starting to break down the water, Challoner explained when discussing the hotspot findings. That had been predicted by theory, but it's really exciting to actually see this with real observations. This might seem like a small distinction. Theory predicted it, observations confirmed it. But in science, the gap between "we think this happens" and "we watched it happen" is enormous. It's the difference between a detective theorizing about a crime based on evidence and actually having video footage of the event. The 3D map didn't just confirm theories, it revealed the messy, complex reality that even the best models can't fully capture. Megan Weiner-Mansfield, assistant professor of astronomy at the University of Maryland and co-leader of the project, put it in perspective. We've seen this happen on a population level, where you can see a cooler planet that has water and then a hotter planet that doesn't have water. But this is the first time we've seen this be broken across one planet instead. It's one atmosphere, but we see cooler regions that have water and hotter regions where the water's being broken apart. This distinction is crucial. Previous observations had shown that hot planets tend to have less water vapor than cooler ones, a general trend across many planets. But WASP-18b revealed that this process happens in different zones within a single planet's atmosphere. It's not just that hot planets lose water, it's that within one planet, you can have regions where water exists and regions where it's being actively destroyed, all visible in the same atmospheric map. The technique that made this discovery possible is called spectroscopic eclipse mapping, or 3D eclipse mapping, and it's one of the most ingenious observational methods in modern astronomy. To understand why it's so clever, we need to understand the fundamental problem it solves. Exoplanets are impossibly difficult to observe directly. Even with the most powerful telescopes humanity has ever built, most exoplanets are simply overwhelmed by the light from their parent stars. A typical hot Jupiter emits less than 0.1% of the light we receive from its star system. It's like trying to study a firefly hovering next to a searchlight from several football fields away. You know the firefly is there, but the searchlight makes it impossible to see clearly. Traditional solutions to this problem involve coronagraphs, devices that block the star's light, or waiting for the planet to pass in front of the star and analysing how starlight filters through the planet's atmosphere. Both techniques have been incredibly successful, but they have limitations. Coronagraphs only work for planets that are relatively far from their stars, and transit spectroscopy gives you an average measurement across the entire planet's atmosphere as seen from our viewpoint. Eclipse mapping takes a different approach entirely. Instead of trying to block the star's light or measure starlight passing through the planet's atmosphere, it measures the planet's own infrared light, the heat it radiates into space, and tracks how that light changes as the planet disappears behind its star. Here's how it works in practice. Imagine watching WASP-18b from Earth as it orbits its star. Every 23 hours, the planet passes behind the star from our perspective, an event called a secondary eclipse. As this happens, different parts of the planet disappear from view in sequence. If the planet is moving behind the star from left to right, the left edge vanishes first, then progressively more of the planet is hidden, until finally the whole planet is behind the star and we can't see it at all. During this disappearance, the total infrared light we receive from the system gradually decreases, but it doesn't just decrease uniformly. The amount of decrease depends on how bright each part of the planet is as it disappears. If a particularly hot, bright region vanishes behind the star, the light drops more dramatically than when a cooler, dimmer region disappears. By measuring the precise changes in brightness during the eclipse with exquisite timing, astronomers can essentially work backwards to figure out which parts of the planet were emitting how much light. It's similar to how you might determine the colours in a painting by watching it be slowly covered by a curtain and noting how the overall colour of the visible portion changes as each section is hidden. But the real genius of the technique comes from measuring this process at many different wavelengths of infrared light simultaneously. This is where the 3D part comes in. Different wavelengths of infrared light probe different depths in an atmosphere. This happens because atmospheric molecules absorb light at very specific wavelengths. Water vapor, for example, strongly absorbs infrared light at certain wavelengths like 1.4 and 1.9 micrometers. At these wavelengths, the light can only escape from the upper atmosphere where there isn't much water vapor above to absorb it. But at wavelengths where water doesn't absorb much, the light can come from deeper in the atmosphere. By observing the eclipse at dozens of different wavelengths simultaneously, which the James Webb Space Telescope's instruments can do, astronomers can build up a three-dimensional picture. Some wavelengths show the cool upper atmosphere, others penetrate to reveal the hot lower layers. Combine all these measurements, and you get a temperature map that varies with latitude, longitude, and altitude. If you build a map at a wavelength that water absorbs, you'll see the water deck in the atmosphere, whereas a wavelength that water does not absorb will probe deeper, Challoner explained. If you put those together, you can get a 3D map of the temperatures in this atmosphere. The team's work built on a foundation they had established in 2023 when they published the first 2D eclipse map of WASP-18b using a single wavelength of light. That earlier map was groundbreaking, the first of its kind, but it could only show temperatures across the planet's surface, like a weather map shows temperatures across a continent. The new 3D map adds the crucial vertical dimension, revealing how temperature and composition change with altitude through the atmosphere. What the 3D map revealed is a planet that's extreme in nearly every measurable way, with an atmospheric structure shaped by forces that don't exist in our solar system. The planet's day side, the hemisphere permanently facing the star due to tidal locking, shows a clear pattern. At the very centre, directly in the path of the star's most intense radiation, sits a circular hotspot. This is where temperatures peak at nearly 5,000 degrees Fahrenheit, hot enough to melt most rocks and vaporize many metals. Iron melts at about 2,800 degrees Fahrenheit, gold at 1,945 degrees. Both would be liquid or even gaseous in WASP-18b's hotspot. Surrounding this central inferno is a cooler ring, though cooler is extremely relative. We're still talking about temperatures of several thousand degrees, hot enough to kill you instantly in countless unpleasant ways. But compared to the hotspot, these outer regions are several hundred degrees cooler, creating a distinct temperature gradient across the visible disk of the planet. This pattern tells us something fundamental about the planet's atmospheric dynamics. On Jupiter, powerful jet streams, winds that can exceed 400 miles per hour, efficiently mix the atmosphere and transport heat around the planet. This mixing creates the relatively uniform temperature bands we see at each latitude on Jupiter. But on WASP-18b, the winds apparently aren't strong enough to redistribute the heat away from where it's being deposited. The hotspot stays hot, concentrated where the star's rays hit most directly. Why are WASP-18b's winds weaker than Jupiter's? The answer likely relates to tidal locking. Jupiter rotates once every 10 hours, creating strong Coriolis forces that organize winds into east-west jet streams. WASP-18b, by contrast, doesn't rotate relative to its star at all. It's locked in synchronous rotation, the same way our moon always shows Earth the same face. Without that rotation, the Coriolis effect is minimal, and winds don't organize into the same pattern of strong jets. The vertical structure of the atmosphere revealed another surprise. As you go up in altitude from the deep, dense lower atmosphere to the thin upper layers, temperatures don't just decrease uniformly. Instead, there are distinct layers with different thermal properties, likely corresponding to different chemical compositions. Some altitudes are dominated by water vapor, in regions cool enough for it to survive, others by carbon monoxide, others by hydrogen and helium. Each of these gases absorbs and emits heat differently, creating a layered structure in the atmosphere's temperature profile. And then there's the water, or rather, the lack of it in certain regions. Perhaps the most unexpected finding was the detailed view of water destruction happening in real time across the planet's atmosphere. This discovery illustrates perfectly why direct observations trump even the best theoretical models. Across most of WASP-18b's dayside atmosphere, spectroscopic measurements clearly showed the presence of water vapor. At the extreme temperatures of several thousand degrees Fahrenheit, any water that existed as ice or liquid when the planet formed has long since evaporated. The water exists as a hot, gaseous component of the atmosphere, mixed with hydrogen, helium, carbon monoxide, and other gases. But in the central hotspot, the spectroscopic signature of water vapor becomes significantly weaker. Not absent entirely, the measurements aren't quite sensitive enough to say there's zero water there, but markedly reduced compared to the surrounding regions. This is the water destruction zone, where temperatures exceed the threshold at which water molecules can survive. The chemistry of what's happening here is fascinating. A water molecule consists of one oxygen atom bonded to two hydrogen atoms, H2O. The bonds holding these atoms together are quite strong. On Earth, across the range of temperatures we experience, water remains stable whether as ice, liquid, or vapor. The molecules stay intact. But chemical bonds aren't infinitely strong. They're held together by electromagnetic forces, and those forces can be overcome if you hit the molecules hard enough. At extreme temperatures, molecules move faster and collide with more energy. At around 4,500 to 5,000 degrees Fahrenheit, exactly the temperature in WASP-18b's hotspot, collisions become violent enough to break the oxygen-hydrogen bonds in water molecules. When a water molecule breaks apart, the products depend on the local environment. In the oxygen-rich upper atmospheres of planets, you might get separate hydrogen and oxygen atoms. In deeper regions, the hydrogen atoms might quickly pair up to form molecular hydrogen, H2, while oxygen atoms react with carbon to form carbon monoxide, CO, or carbon dioxide, CO2. Hydroxyl radicals, OH, water molecules missing one hydrogen atom, might form temporarily, but they're highly reactive and quickly participate in other chemical reactions. The result is a complex dynamic atmospheric chemistry that varies dramatically from place to place. In the cooler outer regions of the dayside, water vapor is stable and abundant. But in the central hotspot, water is continuously being destroyed, its constituent atoms recycled into other molecules. There's probably a transitional zone where water molecules are constantly being broken apart and reformed, creating a chemical equilibrium between water and its dissociation products.
This level of detail, seeing the exact regions where water survives and where it doesn't, all mapped in 3 dimensions, was beyond what anyone expected to achieve. It's not just that the map shows temperature variations, it shows the chemical consequences of those temperature variations, region by region. That had been predicted by theory, but it's really exciting to actually see this with real observations, Challoner noted. The difference between prediction and observation might seem subtle, but it's actually profound. Predictions are only as good as your models, and models make assumptions. They simplify. They might miss important effects. Direct observations tell you what's really happening, assumptions and simplifications aside. None of this would have been achievable without the James Webb Space Telescope, arguably humanity's most sophisticated space observatory. Webb represents the culmination of decades of planning, engineering, and scientific ambition. And it's worth taking a moment to appreciate the technological marvel that made this discovery possible. Webb's journey began in 1996, when astronomers first proposed a large infrared telescope to succeed the Hubble Space Telescope. Over the next 25 years, the project faced numerous technical challenges, budget overruns, and schedule delays. The original launch date of 2007 slipped again and again, as engineers grappled with the unprecedented complexity of the design. By the time Webb finally launched on December 25, 2021, it had become the most expensive scientific instrument ever built, with a total cost exceeding $10 billion, but the results have justified the investment. Webb's capabilities far exceed anything that came before. The telescope's primary mirror measures 6.5 meters across, nearly 3 times the diameter of Hubble's mirror. But more important than the size is the wavelength range. Hubble primarily observes invisible and ultraviolet light, the same wavelengths our eyes see. Webb, by contrast, is optimized for infrared wavelengths from 0.6 to 28 micrometers. This is crucial for exoplanet science because hot planets like WASP-18b emit most of their light in the infrared. The mirror itself is an engineering masterpiece. Rather than a single piece of glass, it consists of 18 hexagonal segments made of beryllium, a metal chosen for its lightweight, high stiffness, and excellent performance at extremely cold temperatures. Each segment is coated with a microscopically thin layer of gold, about 100 nanometers thick, or roughly 1,000 times thinner than a human hair, because gold is highly reflective in the infrared wavelengths Webb observes. The segmented design solved a critical problem: how to launch a 6.5-meter mirror when the largest available rocket fairing, the protective nose cone, is only about 4.5 meters wide. The answer was to fold the mirror, then unfold it once in space. The segments are mounted on a backplane with motors that allow each one to be individually positioned with incredible precision, accurate to within about 10 nanometers, or about 1/10,000th the width of a human hair. Webb orbits at the second Lagrange point, or L2, about 1 million miles from Earth on the side opposite the Sun. This location is gravitationally stable. It takes relatively little fuel to maintain position there, and it allows Earth and Sun to always be in the same direction, simplifying thermal design. Between Webb's instruments and the Sun-Earth hangs a massive sunshield, about the size of a tennis court, made of 5 ultra-thin layers of metallized plastic. This sunshield keeps the telescope's optics and instruments at about -380 degrees Fahrenheit, essential for detecting faint infrared signals without being swamped by the telescope's own thermal emission. The instrument that captured the observations of WASP-18b is called NIRISS, the Near Infrared Imager and Slitless Spectrograph. This instrument was contributed by the Canadian Space Agency and is specifically designed for exoplanet observations. It can capture entire spectra, all wavelengths from 0.8 to 2.8 micrometers simultaneously, without requiring the light to pass through a narrow slit first. This slitless spectroscopy mode is crucial for eclipse mapping, because you need to capture every available photon during the brief time the planet is disappearing behind its star. Every aspect of Webb's design, from the choice of metals for the mirror, to the 5-layer sunshield, to the orbital location a million miles from Earth, contributes to making observations like this 3D map possible. It represents not just a triumph of science, but of engineering, project management, and international cooperation. The successful 3D mapping of WASP-18b isn't just about one planet. It's about opening a new window into understanding exoplanets as a population. Before this technique, our understanding of exoplanet atmospheres came primarily from one-dimensional spectra. We could measure the average temperature, the average composition, maybe separate day-side from night-side measurements, but we couldn't see the details of how temperature and composition vary across the planet's surface and with altitude. It's like the difference between knowing the average temperature in the United States is about 52 degrees Fahrenheit, true but not very useful, versus having detailed weather maps showing that it's hot in Phoenix, cold in Alaska, and somewhere in between in Kansas. With 3D mapping, we can start asking much more detailed questions. Why does heat accumulate in some regions and not others? How strong are the winds, and how do they vary with latitude and altitude? Where do clouds form, and how does that affect the temperature structure? What chemical reactions occur in different regions, and how do they depend on local conditions? For WASP-18b specifically, the map revealed patterns that will inform theoretical models for years to come. The weak wind speeds that allow the hotspot to persist without redistributing heat, the vertical temperature structure that hints at layered composition, the real-time water destruction creating different atmospheric zones. All of these observations constrain and test models, helping us understand not just WASP-18b, but hot Jupiters in general. And hot Jupiters, despite being unlike anything in our solar system, are crucial to understanding planet formation and evolution. These planets almost certainly didn't form where we find them. It's too hot close to the star for gas giants to assemble. Instead, they likely formed farther out and migrated inward, a process that may have disrupted or ejected other planets in their systems. Understanding how hot Jupiters behave and why they have the properties we observe helps us understand this migration process and its consequences. The technique also offers a path forward for studying smaller, cooler planets, the ones that might actually be habitable. WASP-18b was chosen as the first target because its large size and extreme temperature make it a relatively easy test case. But as the technique is refined and applied to progressively more challenging targets, it could eventually be used to map super-Earths, sub-Neptunes, and maybe even true Earth-sized rocky planets. Imagine creating a 3D temperature map of a rocky planet in its star's habitable zone. Even without detecting specific biosignatures, such a map could tell us whether the planet has an atmosphere, whether it's thick or thin, whether heat is being redistributed from day to night, suggesting active weather, and whether there are regions with temperatures suitable for liquid water. All of this information would be invaluable for assessing habitability. This new technique is going to be applicable to many, many other planets that we can observe with the James Webb Space Telescope, Challoner noted. We can start to understand exoplanets in 3D as a population, which is very exciting. One of the most valuable aspects of studying exoplanets is the perspective they provide on our own solar system. WASP-18b
despite being radically different from any planet orbiting our Sun, actually helps us understand Jupiter, Saturn, and even Earth better. Jupiter, for instance, has been studied extensively by spacecraft including Pioneer, Voyager, Galileo, and currently Juno. We know a great deal about Jupiter's atmospheric composition, temperature structure, and wind patterns. But Jupiter's atmosphere is shaped by forces quite different from those affecting WASP-18b. Jupiter receives relatively little sunlight, being 5 times farther from the Sun than Earth is. Most of Jupiter's atmospheric heat actually comes from within. The planet is still slowly contracting from its formation, releasing gravitational potential energy as heat. This internal heat source, combined with Jupiter's rapid rotation, drives the powerful jet streams that create Jupiter's distinctive banded appearance. WASP-18b, by contrast, receives thousands of times more radiation from its star than Jupiter gets from the Sun. Internal heat is negligible compared to the stellar heating. The planet doesn't rotate relative to its star. The result is an atmospheric structure completely different from Jupiter's, with a permanent hotspot on the day side and relatively weak winds. By comparing Jupiter and WASP-18b, 2 gas giants with very different heating and rotation, we learn about the factors that control atmospheric dynamics. How much does internal heat matter versus stellar heating? How important is rotation in organizing winds? These questions are fundamental to understanding not just giant planets, but all planetary atmospheres.
There are also connections to Earth's atmosphere. Despite Earth and WASP-18b seeming to have nothing in common, the basic physics of heat transport, the role of different molecules in absorbing and emitting radiation, the way temperature varies with altitude, these principles apply to all atmospheres. Techniques developed for studying exoplanet atmospheres, including sophisticated computer models and analysis methods, can be adapted for Earth climate science. Similarly, insights from Earth's atmosphere inform our interpretation of exoplanet observations. Even the chemistry of water destruction on WASP-18b has solar system analogues. Water molecules are broken apart by ultraviolet radiation in the upper atmospheres of all the giant planets. On Mars and Venus, photochemistry, chemistry driven by sunlight, plays a crucial role in determining atmospheric composition. The processes are different in detail from what's happening on WASP-18b, but the fundamental principles are the same. While the achievement of mapping WASP-18b in 3D is remarkable, it's important to understand the limitations and challenges that remain. First and foremost, the technique only works for planets that pass behind their stars from our perspective. This is a matter of geometric alignment. The planet's orbit must be aligned edge-on to our line of sight, which happens to be the same requirement for transit observations. For planets whose orbits are tilted relative to our viewpoint, we can't see eclipses, and this technique won't work. Statistically, only a small fraction of exoplanets have appropriately aligned orbits. Second, even for planets with the right orbital geometry, the technique currently works best for large, hot planets. WASP-18b is an ideal target, massive enough to emit a strong infrared signal, hot enough that this emission is intense, and with frequent eclipses due to its short orbital period. Smaller, cooler planets will be much more challenging. A planet twice Earth's size orbiting in the habitable zone would emit far less infrared light, requiring much longer observation times to achieve similar signal-to-noise ratios. Third, the spatial resolution is limited. The 3D map of WASP-18b shows broad temperature zones, the central hotspot, the cooler ring, and vertical structure, but it can't resolve fine details like individual storm systems or small-scale features. The planet is simply too distant and too small in angular size. Future observations with more telescope time could improve this somewhat, but there are fundamental limits to the resolution achievable for such distant objects. There's also the challenge of time variability. The map represents a snapshot, or rather, several snapshots combined from multiple eclipses. If the planet's atmosphere changes over time, if storms develop and dissipate, if cloud patterns shift, those changes could affect the interpretation. Distinguishing real spatial variations from temporal changes requires careful analysis and ideally multiple maps separated in time. Interpretation of the maps requires sophisticated atmospheric models. When we see a hot region,
Is it hot because it's receiving more stellar radiation? Because it has different atmospheric composition that absorbs heat more efficiently? Or because atmospheric dynamics have concentrated heat there? Disentangling these effects requires comparing observations with detailed computer simulations of atmospheric physics and chemistry. Finally, there are practical constraints on telescope time. Webb is the most sought-after observatory in astronomy, with demand for observation time far exceeding supply. Every hour spent observing WASP-18b is an hour not spent observing distant galaxies, studying the atmospheres of planets in our solar system, or pursuing any of the countless other fascinating targets astronomers want to study. Decisions about how to allocate this precious resource involve difficult trade-offs. Despite these challenges, the successful demonstration of 3D eclipse mapping represents a major advance. As techniques improve, as more observation time accumulates, and as future telescopes add new capabilities, these limitations will gradually be overcome. The future of exoplanet atmospheric mapping looks extraordinarily promising, with several exciting directions already in development.
In the near term, the research team is planning additional observations of WASP-18b itself. More data will improve the spatial resolution of the map and potentially reveal time-variable features. Does the hotspot location shift slightly over time? Are there atmospheric waves or instabilities that develop and dissipate? These questions might be answerable with extended monitoring. The technique will also be applied to other hot Jupiters. Each planet will have its own unique characteristics based on its mass, orbital distance, stellar type, and atmospheric composition. Some hot Jupiters show evidence of strong winds that efficiently redistribute heat. Others, like WASP-18b, have relatively stagnant atmospheres. Some have thick clouds of exotic materials, vaporized minerals that condense at high altitudes. By mapping many hot Jupiters, astronomers can begin to understand the full diversity of these extreme worlds and what factors control their properties. One particularly intriguing class is the ultra-hot Jupiters, with temperatures even higher than WASP-18b. At temperatures above 6,000 degrees Fahrenheit, even molecules like carbon monoxide and nitrogen start to dissociate. These planets might have atmospheres where molecular chemistry barely exists, replaced by atomic gases and ions. Mapping such planets could reveal atmospheric physics unlike anything we've previously studied. The really ambitious goal is extending the technique to smaller, cooler planets. Super-Earths, rocky planets a few times Earth's mass, are the most common type of exoplanet in the galaxy. Many orbit in their stars' habitable zones, where temperatures could allow liquid water on the surface. These planets are prime targets in the search for life beyond Earth, but they're also very challenging to study because they emit far less infrared light than hot Jupiters. Advances in several areas could make mapping smaller planets feasible. More efficient data analysis algorithms could extract information from weaker signals. Longer observation campaigns could accumulate more data. Next-generation instruments with even better sensitivity could detect fainter infrared emission. And the Nancy Grace Roman Space Telescope, scheduled to launch in 2027, will bring complementary capabilities that could work in concert with Webb. Roman is designed specifically for exoplanet science, with a coronagraph that can directly image planets and a wide-field instrument perfect for finding new exoplanets. While Roman's instruments aren't optimized for eclipse mapping in the same way Webb's are, the two telescopes could coordinate observations, Roman finding new planets, Webb characterizing their atmospheres in detail. Looking even further ahead, concepts exist for even more ambitious missions. The Habitable Worlds Observatory, still in early planning stages, would be specifically designed to directly image and characterize Earth-like planets. With a large mirror and sophisticated coronagraph, it could potentially resolve surface features on rocky exoplanets, not detailed images like photos, but enough to distinguish continents from oceans, to track seasonal changes, to map cloud patterns. Ground-based astronomy is also advancing rapidly. The extremely large telescope under construction in Chile will have a 39-meter primary mirror, the largest optical infrared telescope ever built. Despite the blurring effects of Earth's atmosphere, adaptive optics systems can partially compensate,
and the sheer light-gathering power of such a large telescope will enable observations impossible with smaller instruments. All of these future capabilities build on the foundation established by discoveries like the 3D mapping of WASP-18b. Each new technique, each new telescope, each new discovery adds another piece to the puzzle of understanding planets beyond our solar system. Stepping back from the technical details, it's worth contemplating what achievements like this mean in a broader context. We live in an era of unprecedented cosmic discovery. Less than 30 years ago, the first confirmed exoplanet around a Sun-like star was discovered. Today we know of more than 6,000, with likely billions more in our galaxy alone. We've gone from wondering whether planets exist around other stars to mapping their atmospheres in 3 dimensions.
This progress isn't just about accumulating facts. It's about fundamentally changing our understanding of our place in the universe. For most of human history, we knew only one planetary system, ours. We had no way to know whether the arrangement of planets in our solar system was typical or unusual, whether the processes that shaped Earth's climate were universal or unique. Now we know that planetary systems are incredibly diverse. Some have hot Jupiters spiraling close to their stars. Others have super-Earths and sub-Neptunes, planet types that don't exist in our solar system at all. Some systems are packed with multiple planets in tight orbits. Others have planets in wildly elliptical or inclined orbits. This diversity tells us that planet formation and evolution are complex processes with many possible outcomes. Every planet we study in detail, like WASP-18b, teaches us something about how planets work. We learn about atmospheric physics, chemistry, dynamics. We discover processes that don't occur in our solar system. We test theories against reality. All of this knowledge helps us understand not just other planets, but our own. It gives context to Earth's climate, Jupiter's storms, Saturn's rings, Mars's thin atmosphere, and ultimately, all of this work is building toward answering one of humanity's deepest questions. Are we alone? While WASP-18b itself is utterly inhospitable to life as we know it, the techniques being perfected on such planets will eventually be applied to worlds more like Earth. The better we understand how to characterize exoplanet atmospheres, how to map their temperature and composition, how to interpret what we see, the better equipped we'll be to recognize biosignatures when we find them. A biosignature is an atmospheric composition that strongly suggests the presence of life. On Earth, the most obvious biosignature is the coexistence of significant amounts of oxygen and methane. Both gases are reactive and would disappear relatively quickly without constant replenishment. The fact that Earth's atmosphere contains both simultaneously is a strong indicator that something, life, is actively producing them. If we found a rocky planet in its star's habitable zone with an atmosphere containing both oxygen and methane, that would be extraordinarily exciting. Not definitive proof of life. There might be geological processes that could produce such an atmosphere, but a very strong candidate deserving intense follow-up study. The techniques being developed now, like 3D eclipse mapping, could potentially not just detect these gases, but map their distribution across the planet, providing additional clues about their origin. The mapping of WASP-18b represents more than just another scientific paper published in a prestigious journal. It marks the beginning of a new chapter in astronomy, one where we don't just detect distant planets or infer their properties, but actually map their weather in 3 dimensions. Think about what this means. We're studying a world 400 light-years away, so distant that light from the planet, traveling at 186,000 miles per second, takes 4 centuries to reach us. The light that NASA's instruments detected left WASP-18b in the 1620s, when the Mayflower was crossing the Atlantic. Yet from that ancient light, encoded in tiny variations in infrared brightness during eclipses, scientists reconstructed a detailed 3-dimensional map of the planet's atmosphere as it existed 400 years ago. This is the power of modern astronomy, to turn photons, particles of light that have traveled unimaginable distances, into detailed knowledge about distant worlds. Every photon tells a story, carries information about where it came from and what it encountered along the way. With the right instruments and clever techniques, we can decode those stories. The researchers who accomplished this, Ryan Challoner, Megan Weiner-Mansfield, and more than 30 co-authors from institutions around the world, represent a new generation of astronomers who have grown up with exoplanets as an established field, rather than a speculative frontier.
For them, the question isn't whether planets exist around other stars. That's been definitively answered. The question is, what are those planets actually like? This technique is really the only one that can probe all three dimensions at once: latitude, longitude, and altitude, Mansfield explained. This gives us a higher level of detail than we've ever had to study these celestial bodies. As this technique is applied to more planets, we'll build up a comprehensive understanding of exoplanet atmospheres as a population. We'll be able to answer questions like, how common are planets with strong winds? How does atmospheric circulation depend on rotation rate and stellar heating? Where do clouds form, and what are they made of? How does atmospheric chemistry vary from planet to planet? And eventually, inevitably, we'll apply these techniques to planets more like Earth. Planets orbiting in the habitable zones of their stars. Planets where liquid water might exist on the surface. Planets where, just maybe, life might have taken hold. When that day comes, and it will come, we'll look back at achievements like the 3D mapping of WASP-18b as pioneering work that made it possible. The first steps on a longer journey toward understanding not just our cosmic neighborhood, but the possibility of life throughout the universe. For now, we can marvel at what's been accomplished. From 400 light-years away, using light that began its journey centuries ago, humans have mapped an alien world in 3 dimensions. We've seen regions so hot they tear water molecules apart. We've measured temperature differences with altitude. We've watched, in effect, alien weather systems that no human will ever visit, but that we can now begin to understand. The universe is vast, full of wonders we're only beginning to discover. Thanks to the ingenuity of scientists, the capabilities of instruments like the James Webb Space Telescope, and the human drive to understand our place in the cosmos, we're finally starting to see those wonders clearly. WASP-18b is just the beginning. There are thousands more exoplanets to study, each with its own story to tell. Some will be similar to WASP-18b, validating our understanding. Others will surprise us, revealing atmospheric phenomena we never imagined. And somewhere out there, perhaps sooner than we think, we'll map a world that shows signs of life. That discovery, when it comes, will be one of the most profound moments in human history. But it will only be possible because of work like this: patient, meticulous mapping of distant worlds, one planet at a time, building up our knowledge and capabilities until we're ready for that ultimate discovery. The future of exoplanet science has never been brighter. The tools exist, the techniques are being perfected, and the discoveries are coming faster than ever. We truly are living in a golden age of cosmic exploration, when distant worlds are finally coming into focus. Thank you so much for listening to this story about one of the most groundbreaking achievements in modern astronomy. If you enjoyed learning about how NASA and its partners mapped an alien world in 3 dimensions and discovered things nobody expected, please consider subscribing to stay updated on the latest space discoveries. We're living in an incredible time, when new worlds are being revealed almost weekly, and there are so many more amazing stories to share. Don't forget to hit that subscribe button so you won't miss future episodes about the wonders of the universe. Until next time, keep looking up.